start recording again. Okay, postage stamp. Yes, that's right. At least it's so I think the view can be customized, but at least you should be able to see something. So what I'm going to cover now is sort of MPI internals, and this and the next lecture will sort of cover both sort of an idea of how MPI works inside, and then how that affects potentially the performance you see, and then also how you can then use that information to hopefully write more efficient code, understanding a bit more about how MPI works. Now, these are generic comments because, of course, I didn't write the MPI libraries. OpenMPI or MPI CH2 or Intel MPI weren't written by me, but these are generic comments. I sort of a good mental model for how things go on. In reality, things will probably be slightly different at a low level, and there will be other optimizations, but these are a reasonably good mental model of at a high level what's going on inside. I think the main thing to stress before I start out now is that MPI is a very old, I mean, MPI was defined over 30 years ago. It's remarkable it's still going. And if it were designed today, it would probably not be designed the way it is now. Computing has changed immensely, not least, for example, 30 years ago, all computers were single processors. You had a single processor, no shared memory. And so you ran single-threaded programs. And that's not true anymore. So some fundamental design issues about MPI would be different now if they were. But this is, some of how MPI is implemented is constrained by how it was defined back then, which was obviously done well because it's still usable now. But you would probably do it differently if you were starting out from scratch today. So okay, let's check. So I am recording these lectures, and they will appear on the website shortly after So I'll talk briefly about the MPI library structure. I'll focus mostly on point-to-point, because if you understand point-to-point, that's probably the core of most MPI programs, send and receive. Talk a bit about, and I actually won't talk about single-sided. This is very little there, but really most of this talk is about how point-to-point communications works, and it's slightly more involved than you might imagine to get things working. So MPI implementations are split into modules, and actually there's quite a sorry, I apologize, I meant okay. I'm getting pop-up notifications on email. I've closed that down. The MPI standard has, well, it grows, but the core of the MPI standard covers point-to-point collectives and other bits and pieces, and so it's fairly a natural decomposition. So there will be, if you downloaded an open source MPI implementation, there will probably be directories corresponding to all of these areas. There may be hidden internal modules, and so one way of thinking about how these implementations work is that MPI is meant to be hardware agnostic. You could run an MPI library, you can run an MPI program on almost any computer, but clearly at some level the MPI library has to interface with the hardware. So there will be some hardware specific stuff, whether it's interfacing to Ethernet or InfiniBand, or doing stuff with a shared memory, or using the Cray slingshot network. But the way the MPI library is designed is a vast amount of the code is hardware independent. So 99% of the lines of code are hardware independent, and there's a very clean division between the hardware independent stuff and when it starts to become hardware dependent. And what is often done is you'll define something like an ADI, an abstract device interface. You will have an abstract model of your networking, your virtual model, and you will basically, the main MPI library will only call these ADI calls, and then to port to a different hardware, all you have to do is to port the stuff below this level. You have to, basically, how do I actually send data from process A on computer A to on computer 1 to process B on computer 2? That will go over, as I said, InfiniBand or or some other network, and that will have to be implemented specifically. But the model is that there's this very low level abstract device interface encapsulating the access to the network, and to port to new hardware, you just have to port that very low level stuff, and then all the high level stuff comes for free. So point-to-point is the core of most MPI implementations. Collectives, I mean, MPI was designed from the start for scientific and technical computational science applications, and so common operations such as OR, reduce, broadcast, gather, scatter were defined as they were defined in the language, in the library, apologies, as collective calls. They may be built from point-to-point calls, they may not. But often they will be, at least the default implementation will use the point-to-point. I'm not going to cover MPIO here, but basically the MPIO library basically builds on the standard implementation called Romeo, which just needs basic MPI calls. And so the large number of point-to-point calls exist. We've already seen MPI, send, we've talked about isend, all these things, but they can often be built from a simpler core set of functions. So there will be a core set of functions doing very simple things like sending n bytes of data from process A to process B, and the higher level things like non-blocking, asynchronous, buffered, and other operations will be built on top of that. So I'll talk point to point. So I don't want to sort of be a bit noddy here, but I think this is a useful model. How are we going to characterize point-to-point performance? We're going to send data from and we're actually going to run immediately after the lunchtime. We're going to run a simple ping-pong code. How are we going to interpret the results? Okay. So I always think, I mean, I'm not a car fanatic, but I think cars are very useful models for computing and parallel computing in particular. So, you know, we've got now the car journey. Okay. My car is parked in the nearby garage. It takes 5 minutes to walk there. Okay. After that, I average 60 kilometers per hour when driving. How long does it take? Okay, so to do a journey in minutes against the distance, it doesn't matter how far I go, it takes me 5 minutes to walk to my car, and then the time is then linear in the distance. Okay, 5 minutes to then simple model. So these two parameters will correspond, when we do message passing, to the latency. And then this will correspond to the bandwidth. Okay. If I plot this on a log scale, it looks a bit different. What you see here is that for for small distances, my time is constant at 5 minutes up to about 1 kilometer or 2, and then it starts to increase. At least on log scale, it looks fairly rapidly. But you can plot it different ways, but definitely you can see that anyway, so this is what I would see, and this is typically what we'd expect to see for the time taken to send a message, where this is the latency, and this is where this is the message size, and this is the time taken. So you get very different small and large distance behavior. For small distances, it takes a constant time of 5 minutes. Okay, so what that's saying is when we go to actual sending messages in MPI, small messages, and we'll come back to what does small mean, will take a constant time. It will take the same number of microseconds to send 1 byte as to send 10 bytes, basically. But long distances, if I plot the speed against the distance, achieve a constant speed. So when I drive a long distance, I have the latency of 5 minutes. The overhead is negligible. I achieve a constant speed. So small distances take constant time. Long distances achieve constant speed. And in MPI terms, small distances will take a constant latency of a certain number of microseconds, and long messages will achieve a constant bandwidth asymptotically of hopefully tens of gigabytes per second. So I've talked about long and small and large. What does that mean? Well, a very useful measure is what I got n.5 when it takes equal time as driving as walking. Okay, so n.5 is the speed times the latency. It's 5 kilometers. If I travel 5 kilometers, okay, I spend equal number of time getting to the car as driving. So you'll see that the time against the distance starts to change about 5 kilometers, and then much above 5 you get constant speed. So this when you say small message, what do you mean? Well, this n.5, where you spend the equal amount of time in the overhead and it's actually doing the transfer, walking and driving, or latency and bandwidth, gives you a useful measure as to where the change in behavior is likely to be. So for point-to-point MPI, latency is the overhead of sending any message, the time to get a very short message on the network, probably about a microsecond. And in practice, that's actually often software overheads rather than hardware overheads. The bandwidth is the rate of transfer on the network. Here I assumed it's 10 gigabytes per second. So if I plot the time taken to send a message against the message size, it starts off always at 1 microsecond. That's a fairly generous assumption, and then it starts to go up. Or for large messages, I achieve a constant bandwidth of 10 gigabytes per second. And the crossover here, n.5, is 10 kilobytes. So you can see here that so I would say with these two parameters of 1 microsecond latency and 10 gigabytes per second of bandwidth, then 10 kilobytes would be my crossover between small message and large message behavior, constant time versus constant bandwidth. So that's just a useful analogy. MPI defines a lot of communication modes, probably too many. I mean, when MPI was defined, they were trying to basically encompass all the message passing libraries which had gone before it for portability issues. And MPI defines multiple types of send, but there are two clear types of send. One is buffered, and although people very rarely call this explicitly, it's MPI B send, buffered send. What happens is it's like sending an email. Your buffered send completes locally whether or not match and receive have been posted. In other words, when you make a buffered send, it's like sending an email. You just send it and then you just fire and forget. However, it's called buffered send because to do this fire and forget model, MPI has to take a copy. They just buffered somewhere until the receive is posted. And the reason, it's a bit technical, but why people tend not to use buffered sends is buffering send fails if insufficient buffering space is provided. It's actually up to the user to provide the buffering space. So if you provide a megabyte of buffering space and try and send 2 megabytes of message, then MPI will fall over and complain. Synchronous is like making a phone call. Synchronous sends can only complete when the match and receive has been posted. That in MPI is MPI S send, and that's like making a phone call. You pick up the phone and you wait on the phone until someone picks up at the other end. You wait until the receive is posted, and that clearly can lead to deadlock, but does not require any copying. Okay, so you'd want to do that for large messages where you might not want to copy. You might not have room to copy the data locally. MPI also describes ready send. It's mad. Okay, it's ready send. Ready send, which nobody ever uses, and I don't even mention it anymore in my introductory course, it requires there to have been a receive already posted. It's madness, and you should never use it. So it's only there for historical reasons, I think. The what I really want to concentrate here is standard send. Okay, so standard send is what most people use, MPI send, and somewhat strangely, standard send can be either buffered or synchronous, depending on the availability of buffer space. And so you might ask, if I do standard send, you think I can do explicitly buffered sends in MPI, where MPI takes a copy of the message, returns control to me, and delivers the message sometime in the future. I can do explicitly synchronous sends, where it's like making a phone call. MPI synchronous send waits until the receive is posted. There's no explicit copying, but does not return control to me until the receive has been posted, in which case I could get deadlock if the receive was never posted. The obvious question is MPI send, standard send, buffered or synchronous? Well, you don't know. And the logic is let MPI decide. That's the kind of formal logic. Don't tell MPI whether to do synchronous send or buffered send. Let it decide and what it thinks is best. And what this allows MPI to do in practice is that for small messages, standard send is buffered. It takes a copy and returns control to you. For large messages, it becomes synchronous, and it waits for, it says, well, I'd like to be buffered, basically, because that's nice. It means that the sender can get on doing other stuff straight away. But maybe I don't have enough buffer space. And so if I don't have enough buffer space, I won't buffer the message. I will become synchronous. I'll wait for the receive to be posted. So, so you should not assume when you issue an MPI send, okay, you should not assume that buffering takes place, but you should also not assume that it doesn't take place. You should not assume that if when the standard send returns, you don't know if the message has been received or not. It might have, it might not. And this is MPI trying to be helpful, but it does cause a lot of confusion. And so we'll come back to how that is actually translates into what MPI does under the hood. Another few things which you may never have thought of, but which actually affect how MPI is implemented. MPI requires ordering. Message sent between two endpoints must be non-overtaking. That actually is it's interesting. You never really think about that, but if MPI messages were not ordered, then it would be almost impossible to write a correct program, because you'd send a message with some data, send another message which says I'm finished, and the I'm finished message might overtake the here's some data message. So that actually is quite important. We often don't think about it. Fairness. MPI does not guarantee fairness. Fairness means, for example, if I issue a receive from MPI any source, it will receive messages from equally from all senders. Of course, it might preferentially always receive from rank 0. So message tags help that ordering. So yeah, so in older message passing systems, because remember, message ordering is not guaranteed at the hardware level. When you send a message over a modern network, it's split into packets. The packets take different routes and are reassembled at the other side. And early message passing libraries often didn't enforce message ordering, and so people would tag the messages themselves. However, you very rarely need tags, and the reason you don't need tags is because the messages are ordered. So if you do 2 sends and 2 receives, they will match in the order they were sent. So actually, you could use tags, but often you don't need to if you know that messages are ordered. I'll have an example slide later on, maybe illustrates that. But yes, tags can help the ordering, but in practice, you often don't need them. If you know them, if you understand that messages are ordered, then you don't need tags, because you have a guarantee of what order they arrive in, or what order they'll be received in regards to the tag. The exercise we're going to do after lunch will allow us to infer that it can be configured there will be some magic environment variable, MPI eager limit. It's probably about 10 kilobytes, something like that. A few tens of kilobytes is sort of a standard figure. It can be configured, but not in a portable way. There will be some magic MPI-CH environment variable which allows you to configure it. On ARCHER2, it's even more complicated because the buffer size, large messages are split into lots of small messages, which are each individually buffered. So when you have a buffer size of 10 kilobytes, actually messages of 100 kilobytes can be buffered because it splits into 10 separate messages. It's slightly confusing, but about 10 kilobytes is about, I would guess, a sort of standard figure. Does that help? Yeah. There should be a finite level of the resources required to process each message. That's why MPI send cannot guarantee to buffer every message, because that would mean it would have to be able to buffer an infinite number of messages. Progress will come back to this, but outstanding communication should be progressed where possible. And we'll come back to that. But basically, it means that, I'll talk about progression here. So this is a slightly contrived, it's a very contrived example, but what I'm doing is rank 1, okay, is issuing a non-blocking receive, okay, and then it immediately goes into the barrier, okay. So there is a receive set up. So the non-blocking says, I'm expecting some data from rank 1, okay, please set up a non-blocking receive. Then it goes into the barrier. Rank 0 then sends to 1 with an MPIS send. So rank 1 is sitting here in the barrier. Rank 1 is not allowed to sit there in the barrier saying I'm in a barrier. Rank 1 or MPI is obliged to progress. When you think rank 1 is in the barrier, it's not sitting in the barrier. It's actually basically going, well, I'm in the barrier, but I better check. I've got this outstanding non-blocking receive. I better check. So what it's doing is it's basically checking all the time actively to see if there's any incoming messages, because it has to progress them. Because if it didn't progress the send from rank 0 would never get to the barrier and you would get a deadlock. So you might think that when you call a barrier, it sits in the barrier. It doesn't. What it's doing is it's actively busy waiting and checking for lots of stuff going on. Oh, there's an outgoing message I can progress. There's something coming in. There's stuff going on. So it's doing lots and lots of stuff. So it's basically doing a lot of stuff. Okay. So often what MPI does is basically when you call an MPI routine. So the other thing I should say is that MPI libraries are typically single-threaded. So you think of there being MPI being a universal, always active postmaster or postmistress delivering your data. Actually, it's not. The only time MPI can do anything is when you call the library. So when you call any MPI call, like MPI Recv or MPI Send, the first thing it does is it ignores what you've asked it to do. It goes away and says, right, what stuff is going on? What do I need to take care of? Okay, so it's like a manual interrupt. And again, if MPI were defined today, it wouldn't be done. It wouldn't be done like that. Use multi-threading. But I have some example later on. But message progression, MPI it can't just sit there waiting in the barrier. It has to actively progress things. MPI divides both blocking and non-blocking calls. Blocking calls say, please send this message and return to me when you've done it. Non-blocking says, send this message sometime in the future, give me back a handle or request, which allow me to say later on, has the message been delivered? Actually, low-level network protocols typically are actually non-blocking. So actually, the native thing for a network is probably non-blocking. And as I said, when I say blocking, when I say please send this message, if I do synchronous send, conceptually MPI is sitting there waiting for someone to pick up the phone. In practice, it's probably running around doing lots of bookkeeping. So it's slightly subtle, but I think it's important to understand that blocking and non-blocking both exist. But it's an interesting point that although we think of blocking as the obvious thing and non-blocking is slightly complicated, at the network level, most networks natively use non-blocking calls to allow them to do lots of things at once. I've lost my cursor. So point-to-point example, if I'm doing a halo swapping, okay, I want to receive data from my up neighbor, receive data from my down neighbor, send to my down neighbor, and send to my up neighbor. I want to do a send and a receive. The problem with MPI is if I did MPI receive here, okay, then this would deadlock, because it would be because everyone would be sitting in the receive and nobody would get into the send. Okay, that's the problem about blocking calls. If everybody calls the receive first, and if you want to do the receive first, if everyone calls the receive, everyone's sitting in the receive saying where's the send, but nobody's going to the send. Okay, you get this catch-22. So that's where you use non-blocking. You say, please, I'm expecting some data from my up neighbor. I'm expecting some data from my down neighbor. Okay, but basically, return control to me, issue a non-blocking call where I get a reference to this communication in this request, which is like a ticket, and then I can do the sends down and up. Which match, and then I have to wait for these to complete. So this means that I know at this point that my send has gone down and my send has gone up. I don't know if this data has been received, so I have to wait on these to complete. And that's why you use non-blocking. It's to avoid deadlock. Coming back to what Mark said about ordering, you might worry that if you're running this on, say, 2 processes, your up and your down neighbor are the same process. Okay, so you're saying I want to receive 2 messages. So you're doing on rank 0 and rank 1. And I've got cyclic boundary conditions. My up neighbor, if I'm rank 0, my up neighbor and my down neighbor are both rank 1. Okay, so I'm receiving 2 messages from rank 1, okay, and sending 2 messages to rank 1. How do I make sure that the correct receive matches the correct send? Well, I could use tags, but actually, if I order them, then because the first receive I issue from my up neighbor, okay, is received from my up neighbor, my first send is to the down neighbor. And so because I've carefully ordered these, this code will always work. if I hadn't carefully ordered them, it could potentially have gone wrong on small numbers of processes where my up and down neighbor are the same. And in that case, I could have used tags. But you don't have to use tags if you understand how message matching works. So it's important that that send down is guaranteed to match that receive up, because that receive was posted first. So even if the down neighbor and the up neighbor are the same, then this code will work. That's a slight subtlety, and the main reason here is to show why you use non-blocking communications. MPI also has persistent communications. It's a bit strange in MPI that every time you call it, if you do halo swapping, you're calling an MPI send of a particular buffer to the parameters to your send are the same, and you call it millions of times. Okay, so MPI also defines persistent communications, where you say, here's an operation I want to do lots of times. So you initiate it, and then you say, do that operation. In practice, that doesn't help much, because for point-to-point communication, the overhead of processing the argument list is pretty small. For collectives, there's a lot more that can be done. Okay, if you call it all reduce, there's 101 different algorithms that MPI could use to do that, and which is the most efficient will depend on how many processes you're running in, how big the buffer sizes are. And so persistent collectives are now a part of MPI, but they have actually been, persistent operations have been a part, I have an example later on, have been a part of MPI for many years, but they weren't much use. Persistent collectives are in principle very useful, because they allow MPI to say, David wants to do, by saying you're doing something persistent, you're saying MPI, I'm going to do this lots and lots of times. So MPI can then say, well, it's worth me going away and trying up 50 different ways and working out what the best way is. And the way that persistent works is you don't do MPI I receive, MPI I receive, MPI send. You say MPI receive init. You say, I am going to want to do this operation in the future. I'm going to want to do this in the future. And these requests then, so this doesn't do the send and the receive. It just says, I'm going to want to do these with all these arguments, these buffers and these counts and these data types in the future. You get back these requests which refer to these, and then you do MPI start all. This says start them all. So again, for point-to-point, it's probably not worth the effort, but for collectives, it may be worth the effort. There is a slight caveat here that the order of persistent calls is not guaranteed. So when you start all, it can start them in any order. That means to get correct message matching, you have to use tags. It's a bit of a, but persistent calls, I mean, they're not commonly used, but they may be useful if you're doing lots of collectives. It depends on the quality of the implementation. We've talked about derived data types. In most MPI implementations, the very low level abstract device interface calls are just allow you to send a certain block of bytes from A to B. So the way that derived data types work is MPI does actually do an explicit copy. You can argue whether it might be, someone's asked this question already, is it quicker to do the copy yourself with that fortran array syntax? It might be. I still think derived data types are very useful for elegance, and they should be implemented reasonably efficiently. But it is worth realizing that there's not really any magic going on at the low level. It is probably copying the data into a contiguous buffer, sending it, and then unpacking. It's doing a pack, send, unpack, copy in, send, copy out mechanism. But the most important part of this lecture is really how does MPI work at the lowest level? How does MPI actually send data from one process to another? And so what will happen is that when you try and send data, okay, MPI needs a mechanism for delivering packets of data to remote processes. They might be your message, but in practice, they might be a protocol message. What this means is if you want to send a message to another process, what might actually happen is that MPI sends a little header saying, there's a message incoming, okay? And then you will just get, that will just notify you that there's a message waiting. They may get back and get the data later, okay? So so whenever a process sends an MPI message to a remote process, what happens is, a good model is it sends an initial protocol message, okay? Now, it may contain some data, but it may also just be, so your go-to model is an MPI process wants to send data to another process. What it does, it actually just sends a little header message of maybe 128, 256 bytes saying, I've got some data for you. Come back to me and receive it when you're ready. So do you mean PVM? Do you mean the pack unpacked, Mark, or the protocol stuff? So yes, PVM was explicit pack unpack model.
Yeah, I'm thinking of the days before 94, before MPI. I think.
Yeah.
So we have to tell it we're going to send.
Yeah, but luckily the data types is done invisibly for you. Yeah. So many implementations use a fixed size header for all messages. What this means is whenever you send data to another process, what will be sent will be a small header message, 128 bytes of data, and there'll be enough field for the envelope. Okay, there's a message waiting from this guy, and it contains this amount of mark. Obviously, if your message is really small, it might be able to fit the data on the protocol message as well. That's your model. Your go-to model should be when I send data. When I send a message to MPI, what's sent is a little header, a little protocol message saying there's some data over here for you. Come and receive it when you're ready. Whoops, sorry. So if the receiving process already has a matching receive, then it can actually go back and say, okay, I want to receive the data, and I know where to put it. If the receive hasn't been issued, what it has to do is it has to park that message and basically put it somewhere and say, well, I've got a send from this guy, but I don't have a matching receive yet. Okay, so that tells you immediately that wherever possible, you should post receives before the sends. It's a lot less work for MPI if the receive exists, because when the send comes in, it can match it immediately. Otherwise, it has to say, well, there's a send coming in, but I don't know what to do with it because I don't have a receive. It has to park it somewhere and process it later on. Also, if you do a receive, when you do a receive call, the first thing you do is say, well, I want to receive data, but maybe I've already had a ping from somebody, you look for it, okay? So again, in practice, there could be lots of different queues, but in practice, MPI tends to have a single global queue. So MPI starts to basically struggle if you have lots and lots and lots of outstanding messages which aren't being received. Okay, because every time it looks like there's a huge queue of messages I have to look through. Okay, that's a sort of a. So how does MPI actually deliver the message? Well, the two most basic ways are eager and rendezvous, and these map quite nicely onto the thresholds of MPI send being buffered or synchronous. Okay, so I'll talk about these. So the eager protocol and there's the rendezvous protocol. And there's lots of variants of these, but if you understand these, you've got some basic model for how things go on under the hood. So the eager protocol, okay, the initial protocol contains the full data for the corresponding MPI message. Okay, so when you want to send data, you basically send all the data. You send the header message and you send the data all the way over to the remote process. Okay, so if there's no matching receive, the data must be buffered at the receiver. So this is what you'd like to do when you do MPI send. What you'd like MPI send to do is to copy the data over to the remote process, get back to you, and then carry on. However, that requires there to be storage space at the remote process, and so that's why this can only be done for relatively small. So what MPI does, it reserves space for incoming messages up to a certain size. So when you send small messages, they will be delivered immediately because you know there is enough buffer space on the other side to send it straight over. Okay, so eager sends can complete as soon as the initial protocol message has been sent. That means what it's saying is if you do an MPI send with a small message size, MPI say that's a small message, I'll copy the data over to the remote process, come back, and the send completes. Okay. Okay. So we'll come back to how MPI com interact with the queues. It basically matches them. So as you could have a different queue for each communicator, but MPI tends not to. Tends to have a single global queue. I'll come back at the end. I don't think it will help make it more efficient. In principle, it would, because you only have to check for messages in that communicator. But in practice, I don't think that's what's done. I'll come back to that. So the eager protocol requires buffering the receiving process. It requires the receiver to have the data already allocated. But that means that, because MPI is only allowed to take up a finite amount of memory, then there has to be a limit on, you can say, I will do eager protocol up to 10 kilobytes, but not beyond. And ready messages I'm not going to talk about. So the rendezvous protocol is kind of the most general but resource intensive. What happens is in the rendezvous protocol, when you send the initial protocol message, it only contains the envelope information. So if you've got to send a gigabyte of data, what MPI does is says, well, I will actually just send a little header. So I'll tell the other guy, I've got data for you. Okay, so that's it's called a rendezvous because you send an initial message. Okay, then when the receiver is supposed to receive, it notices that and then it gets back to you and says, yes, I'm ready for the data, and then it's sent. So the eager protocol is fast because it's fire and forget, it's one copy. The rendezvous protocol, which you have to use for big messages, is slower. You send the protocol message, then the guy gets back to say, I'm ready, then you send the data. So it's there, back, and there again. Okay, so it's a rendezvous because there's a handshake. Okay, so for large messages, actually, the rendezvous can be faster because this is basically when you call MPI send, you're just telling MPI, look, please deliver this message in the most efficient way, and MPI will decide whether it wants to do it asynchronously in the eager protocol, or if it do it synchronously during the rendezvous protocol, and hopefully it will choose to switch over at a sensible point. Okay, the idea is you shouldn't choose, MPI can choose. That does have the unfortunate side effect. You don't know if MPI send is synchronous or asynchronous, but it has the benefit is MPI can choose to deliver messages sent with MPI send in the way it thinks is most efficient. However, the rendezvous protocol, which is there, back, there again, will have a higher latency, but potentially bigger bandwidth. I mean, so we'll see after the break. We'll run a ping pong code and try and pick out these things in practice. So what you tend to see, okay, is that if you plot the time against the message size, for small messages, you will get this quick delivery, relatively constant time, because MPI can just deliver the whole message once. But at some point, when you get beyond this eager threshold, MPI says, well, I have to now do the rendezvous protocol. I have to do, here's some data, get back to you, send it later on, and you'll see this jump. So you see something a bit like this, that for small messages, you get fast delivery, and above some size, which is this eager limit, as it's called, which is maybe a few tens of kilobytes, you'll get a jump, and then you'll get another rise as you have a latency bandwidth model up here. Actually, there may be other, for very short messages, if you're just sending a double precision number, it's 8 bytes. Okay, the obvious thing to do is just to send it on the header. The header probably has some unused space on it. So there will be a third region, which is very small messages. So this corresponds to sending a protocol message and the data at the same time. This corresponds to the rendezvous, where you have to send the protocol message, have an acknowledgement, and then send the data later on. There will possibly be an even faster region here, where you don't even then send any data. You just scribble it on the protocol message. I think of this as being like a postcard. Okay, if you're sending large amounts of information, you have an envelope and you put the data inside. Okay, as a letter. But for very small messages, when you're on holiday, a postcard has the data on the protocol message. Everything's in one place. So there will be at least 3 regions, very small messages, intermediate. So this is where, he gets 2 messages, header and data in at the same time. So I think it is 2 messages. Yeah, I think it is a header sent to the receive queue and the data sent to the buffer space. But that question always occurred. And that is my model. So Jared, that is my model. Okay, it doesn't have to be. You could have variable length headers, in which case an eager message would just be a message with a big header. I don't believe that's what's done. My understanding is that it's typically 2 messages. It's a very good question, and I was slightly evading that discussion because I didn't know the answer, and you picked me up on it. But my model is that it's 2 messages: a protocol message into the receive queue and a data message into the buffer space. Yeah, that's my belief. Yeah, that's my model. That's my model. And in that case, that's why the very short message is even faster, because it is actually, if you can get the data on the header, it is 1 message, yeah, as opposed to 2. That's my understanding. So again, we may have very short message protocols. For very large messages, you can sometimes do direct memory access. What that means is the data goes straight from the sender's memory to the receiver's memory. So you may even get a different protocol for very, very large messages. However, the overhead of setting this up is very high, so we may not see it. But the 3 regions you should be able to see when doing a standard ping pong are very short message, intermediate message, very short message where the data is put on the header, intermediate where my model is 2 messages sent at the same time, a header and the data, and a large message regime above the tens of kilobytes where it's a rendezvous. Here's the header, get back to me, here's the data, and you have to have this handshaking. I'm coming to the end of the time. So collectives, what I would say here is that the reason that collectives were, like all reduce, were defined as single routines in MPI was to allow the MPI library to do them efficiently without you having to do it yourself. So people spend their lives researching efficient collective operations. You don't really care how they're done. You just hope the MPI library does a good thing. And one important thing here is that the collectives don't even have to be implemented in software with MPI calls. For example, a modern network might have a hardware barrier. There might be a barrier call which is done in hardware. So on a network which has a hardware barrier, you would hope that MPI library would say, David wants to do a barrier. I'm not even going to call MPI. I'm going to call this special hardware barrier which exists in this particular network. And it will use lots and lots and lots of tricks. So I mean, this is basically saying use collectives when you can, because they will be implemented efficiently. Often your data access patterns don't actually map onto collectives, but that's why hopefully if I get time to the final lecture today, you'll see that for the advanced use of derived data types can allow you to use collectives when you might think you might not be able to do them. That'll become more obvious when I do it. So the collectives, I'm going to go through this quite quickly, but a typically good collectives a naive implementation of all reduced would be everybody sends their data to rank 0, who adds them up and broadcasts them out, sends them out again. That would scale. That would be P messages on P processors. It would scale linearly. That would be a disaster. Good collectives tend to use things like binary trees or whatever, and hopefully the time scales the log of the number of processors. Okay, so that's typically your model. Typically, most collectives, well implemented, will scale the log of the number of processes, whereas if you did them naively, it would scale linearly with the number of processes. And that's a huge difference, because even on 1,000 processes, log to 1,000 is 10. So usually collectives is already ballpark 100 times faster on 1,000 processes. People only have this back. So I don't really have much experience of building MPI libraries myself, because I've tended to always work on large systems where it's pre-built. How can they show us before? I mean, probably most systems look pretty similar nowadays. Most systems are Linux shared memory nodes with InfiniBand. So I think unless you're building something weird, it would work. That's my guess. I don't actually know, but that would be my guess. I think, yeah, that's a good question. I don't know. As I don't have much experience building MPI libraries myself, because I've always used Yes, so that is why you should pick up the system libraries. Absolutely, yeah, you should pick up the system libraries. But if you are building it yourself, then I actually don't know what tweaks and knobs there are to twiddle now. I have seen a lot of things are actually configurable at runtime. So, for example, if OpenMPI has a bunch of different algorithms which you can use for reductions, they're often choosable at runtime with weird and wonderful environment variables, not at compile time. So I think maybe to try and circumvent that problem, they make a lot of stuff configurable at runtime. So when you build it, you just build it, but then your experimentation is done at runtime. Again, that means you'd have to pick the same parameters. The other reason why you want things to be configurable at runtime is that, you know, it's horses for courses. Some algorithms might work well for one user and not for another, depending on their data patterns. So again, it's a good question. I think a lot more is configurable at runtime now than it used to be. So I've just got a picture of a binary tree. Okay, there you go. I won't talk about process topologies or single-sided, but I will. Oh, so okay. Sorry, this is the slide. So okay. This is the slide that someone mentioned about using. Logically, communicators are independent communication domains. Okay. So communicators, a message sent in one communicator can't be received in another. So you could use separate message queues to speed up matching processes. In practice, most application codes only use a few communicators at once. Maybe. So actually, most implementations use a native. So what we're saying is that although in practice, okay, the communicator is just another tag. Okay. It's different because user tags, you can wildcard on them, but in practice, the MPI implementation will just basically send and receive messages in COM world, basically, but the communicators will be done through some special hidden tag. Does that make sense? So that is how the MPI will do it. It will just be a magic tag, which is added on to the normal tag. So it will not. Yeah, it will use global sets of queues for all sends and receives, but it will pick up the correct communicator because the protocol message will have some magic tag attached to it, which reflects the communicator which was sent from. So I can't remember who asked that question, but you're right. In principle, you could have different queues for each communicator, and that would be a good thing to do, possibly, but in practice, they tend not to do that. I'm not going to talk about process topology or single-sided because people weren't that interested in that. So there's a summary, a bit over time. There are many ways of specifying MPI communication. Which one is fastest depends on what MPI library you're using, what hardware you're using, what ARCHER2 you're using. Performance portability is therefore really hard. It's very hard to write an MPI program which is optimally performing everywhere. My advice is always implement lots of different methods, and each time just test them and pick the best one. You know, as I said, if there's 101 ways, sorry, 101. Half a dozen ways to do halo swapping. Implement them all and just have a go the first time you use a new machine and see which is fastest for you. You know, that is probably what I would say. You know, there are some there are some general rules which will help you, which are things like post receives early so that when the send comes in, they will be there and matching and such like. But it's very hard to be definitive. But again. And again, I have a halo swap benchmark which will run sometime today, which does halo swapping in 6 or 7 different ways, and you can see which one's fastest. Okay, I've overrun slightly. What we're going to do, we'll come back after 12. The idea will be, if I can find my window, stop that. Weird is going on here. Yeah. Hopefully you'll see my window now. Yeah, so we'll come back have lunch till 1:30. It goes 55 minutes at least, and then we're going to run a point-to-point benchmark, a simple ping pong, but hopefully we'll now be able to actually understand the results. And then I'll give a general talk on how you can things you might want to improve on your MPI program, and then yeah, that's the plan for this afternoon. So I'll see you guys again at 1:30, which is a practical till 2, and then the next lecture is 2. We'll be back at 1:30.